Today we're going to talk about Bayes inversion formula. It's named after its discoverer, Mr. Bayes, and it promises to give you some surprises. So let's get into it. First, let me say there's a restriction on what we're going to be doing. We only want to use the Bayes inversion formula when we have dependent events. Dependent events mean that the condition and the events are not independent of each other. They depend on one another. So we have dependent events and conditions. If we have independent events and conditions, Bayes inversion formula just cancels everything out and it just becomes trivial. So we'll just say we have dependent events, use Bayes inversion formula on dependent events. Now let's have some jargon as we usually do. The prior events, little a, b, and c, I'm going to call them the first events. Now, they may be first in time if there is a time factor involved, and these are the ones that occur first. Think of them as occurring first. Little letters for the ones that come first. And secondary events are the ones that occur second, and I'm going to call them capital letters. So when you see little letters, you know they are the ones that happened first, and capital letters, they're the ones that happened second. The situation is the following. We know the prior probabilities. That is, we know the probability that this will happen or this or this. That we can figure out. We can also figure out the conditional probabilities. That is, the probability of what happened second given what happened first. The probability of what happened second when I know what happened first. The probability of what happened second given that I know what happened first. And the little letters are what happened first, so I know I'm either in the A, little a occurred, or little b occurred, or little c occurred, and I can figure out the probabilities of each of these possibilities. Let's take an example and see what we can do with it. Remember the example where we had a box, and in it were 5 cubes, 3 red ones and 2 black ones? Well, the first time I pick a cube, the probability of getting a white one is 3 out of 5. The probability of getting a black one is 2 out of 5. Now I've already picked one. It's either a white one or a black one. If it's a white one, then there's 2 whites and 2 blacks left from which I have to pick. If I pick a black one, then there's 3 whites and 1 black from which I have to pick. And I can figure out those probabilities pretty easy. So if I know what came first, black or white, I get these conditional probabilities. That the probability, given that I have a white one, there are 2 blacks and 2 whites, I have 1/2 for black and white. If a black one was picked first, if I know, given that a black one was picked first, I know a black one came first, then the second one is white with probability 3/4 because 3 out of the 4 are white and 1 out of the 4 is black. So 3/4, 1/4. So these conditional probabilities are all known. The conditional probabilities are known. The prior probabilities are known. Well, what is it we want? What are we trying to get? What do we want? We want what's called the posterior probabilities, the posterior probabilities. And the posterior probabilities, well, we'll get to them. Let's remind ourselves what we know. We know P of little a, B, and C, or whatever. We know the prior probabilities, the probability of what came first. And we know the conditional probabilities, that is, the probabilities of what comes second, given we knew what come first. So if we observed what happened first, we can figure out the probabilities of what's going to happen second. Well, what do we want? What we want are the posterior probabilities, which are, believe it or not, the probability of what happened first, given I know what happened second. What happens first, given I know what happens second. Well, we sort of talked about this when we talked about conditional probabilities. We said we pick the ball, we pick a box, we put it in our pocket. The probability is 3/5 that it's white, 2/5 that it's black. And then a ball falls out, or a box falls out, and we see it's white. What's the probability? And it changed to a half. We saw what happened second, and that changed what happened first. So what we were looking at then was what happened first, given what happened second. And that's what we're trying to find. What happened first, given what happened second. So we want the probability of the little letters, given the capital letters. And sometimes that's not obvious. For the box problem, it wasn't bad, it wasn't hard at all. Sometimes it's very difficult. Let's try it. Let me spell out what the answer is. I know you're not going to like this, but here's the answer. If I want the probability of little a given capital A. Capital A is the condition. I know that's happened. Okay? This is what I want. The posterior probability, it's a probability of a primary given a secondary. First comes the primary, and then given the secondary. I know what happens second. The only things I can use on this side of the equal sign are things that I have. And what I have are conditional probabilities, probability of a capital given a little, and I have the probability of little. Those are the only things I have. So each thing on this side of the equation is a product of those two. It's a product of P of a capital given a little times the probability of a little. Each term is exactly that. Now you'll notice that the only capitals on this side of the equal sign is the same as the capital on that side. So if I say given A, then I always have to have A on this side. And if I'm interested in finding the probability of little a is the primary in the numerator. So the numerator is just the probability of capital A given little a times the probability of little a. The denominator has only capital A's, it has only this style, but it has all the primaries in it. If there are more, they'll be listed also. So now, with that guideline, you know how to write down a Bayes inversion formula. Let's try another one just to make sure we know how to do it. We want C given A. Well, all terms are big given little times little. All the terms. The numerator, well, and all the capitals have to be A. Everywhere there's a capital is an A. And in the numerator, we have probability of capital A given little c, probability of little c. In the denominator, we have capital A's, but the little places have all them possible, A's and B's and C's. Okay, let's try one more. Make sure we know what it looks like. You don't have to memorize this. You'll never have to write one down, but you will have to recognize when one is correct and when it isn't. And it's easy to tell when it's correct because the only terms are the probability of capital given little times the probability of little. Those are the only terms you see. And the only capitals are the capital that's here in the condition on this side is the only capitals involved. And the little on the top is the same as the little here. And in the bottom, all the littles are represented. That's the Bayes inversion formula. I'm not going to derive it for you. We can assume Mr. Bayes did it correctly because it's been checked many, many, many times. As a mathematical formula, if you like mathematical formulas, here's a picture of what it is. If you want a probability of a primary given a secondary, what you have to do is use, for the numerator, the probability of the secondary given the primary times the probability of the primary, where the secondary and primaries are the same as they are here. And in the denominator, what you have is the sum up of all the probability of secondary given primary times the probability of primary. For the same secondary, but each of the possible primaries, all of them are in that sum. As a matter of fact, that denominator is the probability of the secondary by itself. If someone said, what's the probability that the second ball is going to be white, and S is white, then it's just this formula. If I have the conditionals and the priors, I can figure out the probability of the secondary. We're not going to need that one. That's not part of the Bayes inversion formula. This is the Bayes inversion formula right here, and that's what we're going to be using. This is nice to know, but it's not what we're going to be using. Okay, let's get an example now so that the thing hits home. In fact, let me uncover the whole thing. What's happening here is that, let's tell a story, make it interesting. We have a class and we're talking about AIDS and how accurate tests are and things like that. And we say, okay, the nurse is out there, she's giving AIDS tests, and we need a volunteer from this class just to go show us how the steps are done. And little Johnny says, well, I'll go, okay. He's not little, he's a college student, but Johnny goes, and he gets his test. And Johnny's test comes out positive. Now Johnny is terrified. And the nurse says, this test is 95% accurate. It's 95% accurate. Johnny is really terrified. In fact, we're all terrified. We sort of move away from him. Johnny, why don't you sit in the corner of the room? Don't bleed on us, kind of thing. Well, does Johnny have AIDS? What are the chances that Johnny has AIDS? How likely is it that Johnny actually has AIDS? And that's what we're going to attack with the Bayes inversion formula. You see, the having AIDS is the primary. He either has it or he doesn't have it. That's step one. Now there's a test given. The test is either positive or negative. That's the secondary. Given that he has the primary, what's the probability of the secondary? What we really want to know is, knowing that he has a positive test, the secondary, what is the probability that Johnny actually has AIDS, the primary? Okay? Let's do it. Okay, the nurse says that the test is 95% accurate. That means if you have AIDS, it will give a positive reading 95% of the time. 95% of the time. It's 95% accurate, so if you have AIDS, it will be positive 95% of the time. Of course, it's going to be negative 5% of the time. That would be called a false negative. You get a false negative 5% of the time, meaning if you have AIDS, you'll get by with it. You won't have it detected in 5% of the instances. Okay? That's what happens if you have AIDS. What if you don't have AIDS? If you don't have AIDS, you have a false positive 1% of the time. Well, now that's called false positive. Sometimes, in fact, usually, these two numbers are confused. False reading. They say, oh, there's a 1% of a false reading, or 5% of a false reading. This is a false reading, and this is a false reading. Which one are they referring to? Because they don't understand that there's a difference, both of them become 5%. And that's not true. They're totally different things. If someone doesn't have a AIDS, there's no reason why this should be 5%, because this is 5%. So let's say when he doesn't have AIDS, this person who doesn't have AIDS, that means 1% of the people who don't have AIDS will show up positive anyway in this. Hopefully Johnny is one of this 1%. However, if you don't have AIDS, it will be negative 99% of the time. Some people want to say this is 99% accurate test, but we've already said this is what we mean by accuracy, so I don't know what name you'd want to give to that. This is a correct negative 99% of the time. Well, in the general population, 1 in 10,000 people have AIDS. 9,999 do not have AIDS. These are the prior probabilities. These are the conditional probabilities. And what we want is the probability that Johnny has AIDS, given that Johnny has a positive test. So this is the condition, this is the capital A, and this is the little a. And we have to use Bayes' inversion formula. And there are only two things. There's only little a, little b, and capital A, capital B. So it's a really simple equation. In fact, if we have room here, we might be able to write it down. This is the probability of, and we said plus given little AIDS, let's say, times the probability of someone having AIDS, divided by the probability of someone having AIDS given that he has AIDS, times little a, plus the probability that he has AIDS given that he no AIDS, let's say no, times the probability of no. Okay? You might not be able to see that on your screen, but you know what I'm talking about. So that's very simple. That's what the formula breaks down to. And let's do it. Let's actually do the calculation. Here it is again. Here it is. The A, the only capital A, the plus, there's only plus, there's no minuses. AIDS is the little one and it's on the top. But on the bottom you have AIDS and no AIDS. Now if we plug in the numbers, the probability of having a plus test given you have AIDS is 95%. The probability of having AIDS is 1,000th. 1/10 of a percent. Probability of having AIDS, 95, 1,000th, 1%, 0.999. You do the arithmetic, and you get out 0.0094, which is less than 1%. There's less than a 1% chance that Johnny has AIDS. In fact, in spite of the fact that the test was 95% accurate, there is still less than a 1% chance that Johnny has AIDS. I think before he gets terrified, he should have some more testing done. But certainly it's worth having another test made. I wouldn't dismiss it. Even a 1% chance is something we'd want to check into. However, panic is not really called for. Okay, let's take another example, perhaps a little closer to home for some people. And that's the example of breast cancer. Let's say that this data, the numbers on breast cancer are these. I'll uncover them. Let's look at them. Test is 95% accurate. That is, and by the way, this is only for women. This does not include men. A test that's 95% accurate means that if a woman has breast cancer, the test will show it. The mammogram will show it 95% of the time. If she has breast cancer, it won't show it only 5% of the time, so it's a 95% accurate test. If she does not have breast cancer, it will show it 10% of the time, meaning the mammogram will look like you have something. It's probably some calcium deposit or something, but it will show a positive test. It will show the negative test when you don't have cancer 90% of the time. So there's a 10% false error rate and a 95% accuracy. So if we know that it's 95% accuracy and a 10% false error rate, we know all these numbers. Now, in the general population, 1 in 1,000 have breast cancer. 999 in 1,000 do not. So the probability of breast cancer is 1,000, and not having breast cancer is 0.999. Now, this is the data here. Jane goes and takes the breast cancer test, and it's positive. Well, test 95% accurate. Jane says, gee, there's a 95% chance I have cancer. And someone else will come along and say, oh, well, what if you're here? It's 10, somewhere between 10 and 95 anyway. And the answer is no, that's totally wrong. You have to use the Bayes inversion formula. You can't just look at the numbers and sort of come up with a guess. You can't guess at this. You have to work it out. And it's not obvious. So if we work it out, we come up with the formula. Breast cancer given positive test given breast cancer, positive test, breast cancer, positive test, no breast cancer. And plug in the data. 95 1,000th, 10%, 999. Working it out, we end up with, again, a number less than 1%. Less than 1%. In spite of the fact that the numbers we saw banted around were somewhere between 10 and 95. It's less than 1%. Okay, what's going on? What's going on is that finding a posterior probability, that is a probability of a primary given a secondary, is not trivial. It's not hard. You plug the numbers in and you come up with it, but it sort of doesn't follow intuition. And sometimes looking at data, you can sort of be pushed into believing something that's not true. Because the test is 95% accurate does not mean there's a high probability that you have something. A very important ingredient in that is the fact that someone went to take the test. They felt they probably had it, and they went to take the test, and it was positive. That's just an additional thing. Of the people who feel they probably have something wrong with them, and they take a test. Someone goes in to take an AIDS test because they say, hey, there's a good chance I have AIDS. And they go in and take the test. Among that population, there's just a small chance of getting a false positive. Okay, that's why things work the way they do. However, if a person just randomly is tested, then the numbers that we need are the numbers that come from the Bayes inversion formula. So don't pay any attention to just numbers that come out of the air. Work out the formula. It's not all that hard. See you next time.